On a dark, clear night far from city lights, if you look up toward the constellation Andromeda, you can see something extraordinary with your naked eye, a faint, fuzzy patch of light. This isn't a star, a planet, or even a nebula within our own galaxy. It's another galaxy entirely, the Andromeda Galaxy, also known as M31 or Messier 31. At approximately 2.5 million light-years away, Andromeda is the most distant object visible to the unaided human eye, and it's our nearest large galactic neighbor. But Andromeda is more than just a neighbor. It's a cosmic titan, a spiral galaxy even larger and more massive than our own Milky Way, containing over 1 trillion stars compared to our few hundred billion. It's a galaxy with its own rich history, complex structure, and fascinating mysteries. What makes Andromeda particularly captivating is its intimate connection to our own galaxy. These two massive spirals dominate the local group, the small cluster of galaxies we call home, and they are gravitationally bound to each other. Right now, at this very moment, Andromeda is hurtling toward us at approximately 110 kilometers per second, or about 68 miles per second, or about 250,000 miles per hour. In roughly 4 to 5 billion years, these two giants will collide in one of the most spectacular cosmic events imaginable. Stars will be flung into new orbits, gas clouds will collide and ignite with furious star formation, and the two galaxies will eventually merge into a single, massive, elliptical galaxy. Our night sky will be transformed, and if any observers exist on Earth at that time, they will witness a celestial dance unlike anything we can see today. But the story of Andromeda is not just about its future collision with the Milky Way. It's about understanding a galaxy in exquisite detail, from its multiple spiral arms and massive central bulge to its dark matter halo and the supermassive black hole lurking at its core. It's about the hundreds of globular clusters that orbit it, the satellite dwarf galaxies that dance around it, and the stellar streams that trace past mergers and disruptions. Andromeda is a laboratory for understanding how galaxies work, how they evolve, and what fate awaits galactic systems over cosmic time. Before we embark on this journey across 2.5 million light-years of space, drop it in the comments below where in the world you're watching from and what time it is there. Now, let's begin our voyage to the Andromeda Galaxy, exploring its wonders, its mysteries, and its profound connection to our own cosmic home. The 964 AD mystery, a little cloud that changed astronomy. The Andromeda Galaxy has been observed by humans for over 1,000 years, though its true nature remained a mystery until the 20th century. The earliest known written reference to Andromeda dates back to 964 CE, when the Persian astronomer Abd al-Rahman al-Sufi described it in his Book of Fixed Stars as a small cloud. This observation is remarkable because al-Sufi was describing something that, to the naked eye, appears as just a faint smudge, yet he recognized it as distinct from individual stars. For centuries afterward, Andromeda appeared in star catalogues and was noted by various observers, but its nature remained enigmatic. When telescopes were invented in the early 17th century, astronomers could see it more clearly, but they still couldn't determine what it was. It appeared nebulous, cloud-like, leading to its classification as a nebula. In 1612, the German astronomer Simon Marius observed Andromeda through a telescope and provided one of the first detailed descriptions, comparing its appearance to the light of a candle shining through horn. In 1764, Charles Messier, the French astronomer who was compiling a catalogue of objects that could be confused with comets, included Andromeda as the 31st entry in his catalogue, giving it the designation M31. Messier's catalogue was created to help comet hunters avoid wasting time on objects that weren't comets. But ironically, it became one of the most famous catalogues of deep sky objects, including galaxies, nebulae, and star clusters. Throughout the 18th and 19th centuries, telescopes improved, and observers noticed more details in Andromeda. William Herschel, who discovered Uranus and conducted extensive surveys of the sky, observed Andromeda and noted its structure. By the mid-1800s, astronomers using better telescopes could see that Andromeda had a complex structure with what appeared to be dark lanes, suggesting it might be more than just a simple cloud of gas. The true breakthrough came in the early 20th century with photography. Photographic plates could accumulate light over long exposures, revealing details invisible to the eye. In 1887, Isaac Roberts took one of the first photographs of Andromeda, revealing its spiral structure. This was a crucial observation, as it showed that Andromeda wasn't just a formless cloud, but had an organized spiral pattern, similar to what observers were seeing in other nebulae. However, the critical question remained: was Andromeda part of our own galaxy, the Milky Way, or was it a separate island universe, an entire galaxy in its own right? This question led to one of the most important debates in the history of astronomy, known as the Great Debate of 1920, between Harlow Shapley and Heber Curtis. Shapley argued that the Milky Way was enormous and that spiral nebulae like Andromeda were part of it. Curtis argued that spiral nebulae were separate galaxies, each containing millions or billions of stars, and that the universe was far larger than anyone had imagined. The debate was settled in 1923 to 1924 by Edwin Hubble, working with the 100-inch Hooker telescope at Mount Wilson Observatory, then the largest telescope in the world. Hubble identified Cepheid variable stars in Andromeda. Cepheid variables are stars that pulsate regularly, and there's a precise relationship between their pulsation period and their intrinsic brightness. By measuring the period of these Cepheids and comparing their apparent brightness to their known intrinsic brightness, Hubble could calculate their distance. His calculations showed that Andromeda was approximately 900,000 light-years away, far beyond the boundaries of the Milky Way. This was later revised to the modern value of about 2.5 million light-years, but the conclusion was clear. Andromeda was a separate galaxy, and the universe was vastly larger than anyone had thought. This discovery revolutionized astronomy and our understanding of the cosmos. The universe wasn't just the Milky Way. It contained billions of galaxies, each with billions of stars. Andromeda, our nearest large galactic neighbor, became a focus of intense study, a nearby example of a spiral galaxy that could be observed in detail and compared to our own. Hubble's 1,924 photograph that shattered our universe. The Andromeda Galaxy holds a special place in the history of astronomy. It was instrumental in proving that the universe extends far beyond the Milky Way, containing billions of other galaxies. Edwin Hubble's observations of Cepheid variables in Andromeda in the 1,920 seconds settled the Great Debate and opened the door to modern extragalactic astronomy. Since then, Andromeda has been a constant focus of study, serving as a nearby laboratory for understanding galaxies and testing theories of galactic structure, evolution, and dynamics. The study of Andromeda has contributed to numerous discoveries and advances. It provided one of the first examples of a galactic rotation curve extending into the regime where dark matter dominates, helping to establish the existence and importance of dark matter in galaxies. Observations of Andromeda's satellite galaxies have tested theories of hierarchical galaxy formation and the nature of dark matter on small scales. The discovery of stellar streams in Andromeda's halo has provided direct evidence for the accretion and disruption of smaller galaxies, a key process in galactic evolution. Andromeda has also been a testbed for understanding stellar populations and chemical evolution. By observing millions of individual stars and measuring their properties, astronomers have traced the history of star formation in the galaxy, identified distinct populations with different ages and metallicities, and reconstructed the timeline of Andromeda's assembly. These studies have provided a template for understanding how spiral galaxies evolve over cosmic time. The study of the supermassive black hole at Andromeda's center has contributed to our understanding of the relationship between black holes and their host galaxies. The measurements of the black hole's mass and its influence on the surrounding stars have helped establish the correlations between black hole mass and galaxy properties, such as bulge mass and velocity dispersion. These correlations suggest a deep connection between black hole growth and galaxy evolution, though the exact mechanisms are still being explored. Andromeda's role in the local group and its future collision with the Milky Way have also been important for understanding galaxy interactions and mergers. The detailed predictions for the collision, based on simulations, provide insights into what happens when two large spiral galaxies merge, a process that is common in the universe, but difficult to observe directly because it unfolds over billions of years. By studying Andromeda and the Milky Way, and by simulating their future merger, astronomers gain a unique perspective on galactic dynamics and evolution. Looking forward, Andromeda will continue to be a key target for observations. New telescopes and instruments, such as the James Webb Space Telescope, the Extremely Large Telescope, and the Nancy Grace Roman Space Telescope, will provide even more detailed views of the galaxy, revealing fainter stars, more distant structures, and more subtle features. These observations will refine our understanding of Andromeda's structure, composition, and history, and they will provide new tests of theories of galaxy formation and dark matter. The future collision with the Milky Way also ensures that Andromeda will remain a focus of study for generations to come. As the collision approaches, astronomers will continue to refine their predictions, monitor changes in the motions of the two galaxies, and simulate the merger in ever greater detail. The collision is a natural experiment, a unique event that will transform our region of the universe, and studying it provides unparalleled insights into the processes that shape galaxies. Andromeda is more than just a beautiful object in the night sky. It is a window into the nature of galaxies, a key to understanding our own Milky Way, and a reminder of the dynamic and ever-changing universe in which we live. The study of Andromeda connects us to the cosmos, revealing the intricate structures and processes that govern the formation and evolution of galaxies across space and time. Thank you for joining me on this journey to the Andromeda Galaxy. If you enjoyed this exploration, make sure to like this video, subscribe to the channel, and hit the notification bell so you never miss future content. Drop a comment below with your thoughts. What aspect of Andromeda fascinates you the most? Are you excited about the future collision with the Milky Way? And if you want to support the channel and help us create more deep dives into the cosmos, consider becoming a patron or checking out our merchandise. Until next time, keep looking up, keep asking questions, and never stop wondering about the magnificent galaxies that fill our universe. Andromeda is calling to us across 2.5 million light-years, inviting us to explore, to understand, and to marvel at the beauty and complexity of the cosmos. 1 trillion suns in a spiral twice our size. The Andromeda Galaxy is a magnificent spiral galaxy, classified as type SAB in the Hubble sequence, indicating it's an unbarred spiral with moderately wound arms. Its structure is complex and fascinating, with multiple components that reveal its long history and dynamic nature. At the heart of Andromeda lies its central bulge, a dense, roughly spherical concentration of old stars. The bulge extends about 10,000 to 12,000 light-years from the galactic center and contains a mix of stellar populations with ages ranging from ancient to relatively young. The bulge is not uniform, but has a complex structure. Observations have revealed that it contains at least 2 distinct stellar populations, suggesting it formed through multiple processes, possibly including mergers with smaller galaxies in the distant past. At the very center of the bulge lurks a supermassive black hole with a mass estimated at 100 to 230 million times that of the Sunday. This is considerably more massive than the Milky Way's central black hole, Sagittarius A*, which has a mass of about 4 million solar masses. The Andromeda black hole is surprisingly quiet, not actively consuming large amounts of matter, but its presence profoundly influences the dynamics of stars and gas in the central regions. Observations with high-resolution spectroscopy have revealed the velocities of stars near the galactic center, and these velocities indicate the presence of an extremely massive, compact object that can only be a supermassive black hole. To truly grasp Andromeda's enormity, we need to put its size into perspective. The galaxy stretches approximately 220,000 light-years from end to end, making it roughly twice the diameter of our own Milky Way. But what does that really mean? If you could travel at the speed of light, the cosmic speed limit at 186,282 miles per second, fast enough to circle Earth 7.5 times in 1 second, it would still take you 220,000 years to cross from one side of Andromeda to the other. At our current fastest spacecraft speeds, like the Parker Solar Probe, which reached 430,000 miles per hour in 2021, the journey across Andromeda would take over 300 billion years, far longer than the current age of the universe itself. The galaxy contains approximately 1 trillion stars. That's 1,000 billion, or a 1 followed by 12 zeros, twice the estimated 200 to 400 billion stars in the Milky Way. If you could count 1 star per second without stopping, it would take you over 31,000 years to count all the stars in our galaxy, but it would take 63,000 years for Andromeda. Each of those stars represents a sun, potentially with its own system of planets, moons, asteroids, and comets. The sheer number is almost incomprehensible, yet Andromeda is just one galaxy among an estimated 2 trillion galaxies in the observable universe. The total mass of Andromeda is even more staggering. When we account for all the stars, gas, dust, and the massive dark matter halo that surrounds the galaxy, Andromeda weighs in at approximately 1.5 trillion solar masses, meaning it weighs 1.5 trillion times as much as our Sun. That's 1.5 trillion times heavier than our Sun, and the Sun itself weighs nearly 2 nonillion kilograms, or about 333,000 times the weight of Earth. This makes Andromeda the most massive galaxy in our local group, outweighing the Milky Way by a factor of about 1.5 to 2, depending on recent measurements. The double nucleus mystery, 2 hearts beating as one. At the very heart of Andromeda lies one of its most perplexing mysteries. It doesn't have just one nucleus, it has 2. When astronomers first examined high-resolution images of Andromeda's core in the 1,990 seconds using the Hubble Space Telescope, they discovered something unexpected. The bright central point of light that should mark the location of the galaxy's supermassive black hole was offset from the true dynamical center of the galaxy. Nearby, within just 5 light-years, sits another bright concentration of blue stars. This double nucleus has puzzled astronomers for decades. The true center of the galaxy, where the 140 million solar mass black hole resides, appears relatively dim. The brighter, offset peak is actually a disk of hot young blue stars orbiting the black hole at tremendous speeds, reaching over 2.2 million miles per hour. But why is this stellar disk offset from the black hole? And why is it so bright? One leading theory suggests that this structure formed from the disruption of smaller galaxies that Andromeda consumed in the past. As these victim galaxies fell toward Andromeda's center, tidal forces ripped them apart, and their stars settled into an elongated disk around the supermassive black hole. The disk appears offset because we're seeing it edge on from our viewing angle. And the bright blue stars are young, massive stars that formed recently from gas compressed during these ancient collisions. Another possibility is that Andromeda actually contains two supermassive black holes, the remnants of a galaxy merger. If Andromeda collided with another large galaxy billions of years ago, that galaxy's central black hole could have survived and now orbits within Andromeda's core, creating the double nuclear structure we observe. If this is true, these two black holes will eventually merge in a catastrophic event that will release tremendous amounts of energy in the form of gravitational waves. The double nucleus mystery reminds us that even our closest galactic neighbor holds secrets we're still working to understand. Every high-resolution image reveals new details and raises new questions about the violent history hidden in Andromeda's seemingly serene appearance. 14 satellite galaxies orbiting like cosmic moons. Like the Milky Way, Andromeda is not alone, but is surrounded by a family of smaller satellite galaxies. These satellites orbit Andromeda much like moons orbit a planet, bound by gravity to the larger galaxy. Studying Andromeda's satellites provides insights into galaxy formation, the nature of dark matter, and the history of interactions and mergers that have shaped Andromeda over billions of years. The most prominent satellites of Andromeda are M32 and M110, both of which are visible in modest telescopes and appear as fuzzy patches near the main body of Andromeda. M32 is a compact elliptical galaxy, also known as a dwarf elliptical, located about 24,000 light-years from Andromeda's center, projected against the outer disk. Despite its small size, roughly 6,500 light-years in diameter, M32 is quite massive for a dwarf galaxy, with a mass of about 3 billion solar masses. It has a dense core and shows evidence of recent tidal interactions with Andromeda. Some astronomers have proposed that M32 was once a much larger spiral galaxy that lost most of its outer stars and gas during a close passage through Andromeda's disk, leaving behind the compact core we see today. M110, also known as NGC 205, is another dwarf elliptical satellite, located about 200,000 light-years from Andromeda. It is larger and more diffuse than M32, extending about 17,000 light-years across. M110 contains regions of recent star formation, unusual for a dwarf elliptical, suggesting it has retained some gas despite its proximity to Andromeda. The star formation may have been triggered by tidal interactions with Andromeda, compressing gas clouds and initiating the collapse into new stars. Beyond M32 and M110, Andromeda has numerous other satellites, many of them faint dwarf spheroidal galaxies discovered in recent years through deep imaging surveys. As of the early 2022, astronomers have identified over 30 satellite galaxies associated with Andromeda, and the true number is likely higher, as many faint satellites remain undiscovered. These dwarf satellites typically contain only millions of stars, compared to Andromeda's trillion, and they are dominated by dark matter, with mass-to-light ratios far higher than in larger galaxies. The distribution of Andromeda's satellites is not random, but shows interesting patterns. Several satellites appear to lie in a thin plane, aligned with each other in a disk-like structure around Andromeda. This is similar to a pattern observed in the Milky Way's satellites, and is puzzling because the hierarchical model of galaxy formation predicts that satellites should be distributed more isotropically, in a roughly spherical distribution. The planar distribution might indicate that some satellites were accreted as a group, perhaps as part of a larger structure that was tidally disrupted, or it might point to unknown physics in the formation of satellite systems. Some of Andromeda's satellites show signs of ongoing tidal disruption. Stars are being pulled away from the satellites by Andromeda's gravity, forming tidal tails that stretch along the satellite's orbit. Eventually, these satellites will be completely torn apart, and their stars will be absorbed into Andromeda's halo, contributing to the diffuse stellar population and to stellar streams. This process of tidal disruption and accretion has been happening throughout Andromeda's history and is one of the ways galaxies grow over time. The satellite galaxies also provide a laboratory for studying dark matter. Because dwarf galaxies have high dark matter fractions, their dynamics are dominated by dark matter, and observations of stellar velocities within them provide constraints on the dark matter distribution. Some dwarf satellites are so dominated by dark matter that they are referred to as dark matter halos with stars, and they challenge our understanding of how dark matter behaves on small scales. Discrepancies between simulations and observations of satellite properties, such as their abundance and spatial distribution, have led to debates about the nature of dark matter and the processes that govern galaxy formation. The Andromeda satellite system will play a crucial role in the future collision between Andromeda and the Milky Way. During the merger, the satellites will be disrupted and scattered, some being ejected into intergalactic space and others falling into the merged galaxy. The interactions between satellites from both galaxies will add to the complexity and drama of the collision, closing in at 250,000 miles per hour and accelerating. Perhaps the most dramatic aspect of Andromeda is its motion relative to us. The galaxy is not just sitting there in space, it's hurtling toward the Milky Way at approximately 110 kilometers per second, or about 68 miles per second, or about 68 miles per second. To put that in perspective, that's roughly 245,000 miles per hour, more than 300 times faster than a bullet fired from a rifle. At this speed, you could travel from New York to Los Angeles in about 11 seconds, or circle the entire Earth in less than 2 minutes. This measurement was first accurately determined in 1912 by Vesto Slipher at Lowell Observatory in Arizona, making it one of the earliest and most important velocity measurements in astronomy. Slipher measured the Doppler shift, the same effect that makes an ambulance siren sound different as it passes you, of Andromeda's spectral lines, the unique fingerprints of light that each element produces, and found that, unlike most galaxies which show redshift, where light is stretched to longer, redder wavelengths, indicating they're moving away from us, Andromeda exhibited blue shift, where light is compressed to shorter, bluer wavelengths. The light from Andromeda is compressed to shorter, bluer wavelengths because the galaxy is approaching us. This discovery was remarkable because it came 17 years before Edwin Hubble's 1929 announcement of the expanding universe. But here's where it gets even more interesting. While Andromeda is approaching us at 110 kilometers per second, which is about 245,000 miles per hour, this is actually the total relative velocity combining Andromeda's motion through space and our own galaxy's motion. When astronomers account for the sideways motion of both galaxies, they find that Andromeda also has a significant sideways velocity component of about 17 kilometers per second. This means the collision won't be a perfect head-on crash, but rather a glancing blow, which will affect how the two galaxies merge and what the final structure of Milky will look like. The momentum involved in this cosmic collision is almost beyond comprehension. With Andromeda's mass of 1.5 trillion solar masses, meaning it weighs 1.5 trillion times as much as our Sun, moving at 110 kilometers per second, which is about 245,000 miles per hour, the kinetic energy is approximately 9 times 10 quatuordecillion joules. For comparison, the total energy output of the Sun over its entire 10 billion year lifetime is about 10 tredecillion joules. The collision between Andromeda and the Milky Way will release more energy than 1 trillion suns shining for their entire lifetimes. Though this energy will be released gradually over billions of years as the galaxies interact, merge, and settle into their new configuration, our halos are already touching. We're inside Andromeda now. One of the most surprising discoveries about Andromeda came in 2020 when astronomers using data from the Hubble Space Telescope found that the galaxy's halo, a diffuse cloud of gas surrounding the galaxy, extends much farther than anyone had imagined. The halo reaches at least 1.3 million light-years from Andromeda's center, and possibly as far as 2 million light-years. This means that Andromeda's halo already overlaps with the Milky Way's halo, which extends about 1 million light-years from our galactic center. In a very real sense, we are already inside Andromeda's outer reaches. This extended halo contains gas at temperatures of about 10,000 to several million degrees, hot enough to vaporize any material instantly, heated by supernova explosions, where dying stars blast themselves apart with the force of billions of nuclear bombs and the energy released by stars. The gas is extremely tenuous, with a density far lower than the best laboratory vacuums we can create on Earth, but it contains a significant amount of mass, perhaps as much as half the mass of all the stars in Andromeda combined. This gas is enriched with heavy elements, the products of the fusion reactions inside stars that create heavier elements, suggesting it has been expelled from the galaxy by stellar winds and supernovae over billions of years. The discovery of this extended halo has important implications for our understanding of galaxy evolution. It shows that galaxies are not isolated islands of stars, but are surrounded by vast reservoirs of gas that extend far into intergalactic space. This gas can fall back onto the galaxy, fueling new generations of star formation, or it can be lost forever, escaping into the void. The interaction between Andromeda's halo and the Milky Way's halo is already beginning, a precursor to the more dramatic collision that will occur billions of years from now, the 4.5 billion year countdown to collision. One of the most dramatic and fascinating aspects of Andromeda is that it is on a collision course with the Milky Way. In approximately 4 to 5 billion years, these two massive galaxies will collide, merge, and eventually form a single, larger galaxy. This future event has captured the imagination of astronomers and the public alike, and studying it provides insights into the processes that govern galactic interactions and mergers throughout the universe. The fact that Andromeda and the Milky Way are approaching each other has been known since the early 20th century, when astronomers measured the Doppler shift, the same effect that makes an ambulance siren sound different as it passes you, of Andromeda's light, and found that it was blue shift, where light is compressed to shorter, bluer wavelengths, ED, indicating motion toward us. The radial velocity, the component of motion directly toward or away from us, is about 110 kilometers per second, or about 68 miles per second, or roughly 250,000 miles per hour. This might seem fast, but over the vast distance of 2.5 million light-years, it means the collision is still billions of years away. However, determining the exact timing and nature of the collision is more complicated than simply measuring the radial velocity. The full three-dimensional motion of Andromeda includes not just the radial component, but also the sideways motion, the motion perpendicular to our line of sight. Measuring this sideways motion requires precise astrometry, measuring the tiny shift in Andromeda's position on the sky over many years. This is extremely challenging because Andromeda is so distant that its proper motion, its apparent motion across the sky, is exceedingly small. In 2012, astronomers using the Hubble Space Telescope succeeded in measuring Andromeda's sideways motion by tracking the positions of stars within the galaxy over several years and comparing them to the positions of more distant background galaxies. The results showed that Andromeda's sideways velocity is relatively small, meaning that the galaxy is moving almost directly toward us. This confirmed that a collision is inevitable and allowed more precise predictions of the collision's timing and trajectory. The current best estimates suggest that Andromeda and the Milky Way will make their first close passage in about 3.75 to 4 billion years. At that time, the two galaxies will pass through or near each other, and their mutual gravitational attraction will begin to distort their structures. Stars will be pulled out of their original orbits, tidal tails will form, and the collision will trigger bursts of star formation as gas clouds collide and are compressed. The night sky, as seen from Earth, will be dramatically transformed, with Andromeda growing larger and larger until it dominates the view, and eventually the two galaxies will appear to merge and blend together. After the first passage, the two galaxies will not immediately merge, but will swing around each other, pulled back together by gravity for additional passages. With each encounter, more energy is dissipated through tidal interactions and the gravitational influence on stars and gas, and the orbits decay. Eventually, after several passages over the course of another 2 to 3 billion years, the two galaxies will fully merge, settling into a single, massive, elliptical galaxy. This merged galaxy, sometimes humorously referred to as Milkomeda or Milkdromeda, will be one of the largest galaxies in the local group. It will have a total mass of perhaps 2 to 3 trillion solar masses, combining the stellar populations, gas, dark matter, and supermassive black holes of both progenitors. The merger will erase the spiral structures of both galaxies, as the ordered rotation of the disks is disrupted and stars are scattered into more random orbits. The result will be a large elliptical galaxy, with stars moving on a variety of orbital paths, rather than in the organized patterns of a disk. The fate of our solar system during this merger is uncertain, but probably not catastrophic. While the collision involves two galaxies with a combined trillion stars, the distances between stars are so vast that direct stellar collisions are extremely rare. The Sun and its planets will likely survive the merger intact, though they may be flung into a very different orbit. It's possible that the solar system could be ejected into the outer reaches of the merged galaxy, or even into intergalactic space, though this is less likely. If Earth is still habitable at the time of the merger, any observers will witness a spectacular transformation of the night sky, though the changes will occur over millions of years, too slowly for a single human lifetime to perceive. The collision will also have profound effects on star formation. As gas clouds from the two galaxies collide, they will be compressed, triggering intense bursts of star formation. This starburst activity will create numerous young, massive stars, which will light up the merged galaxy and enrich it with heavy elements through supernova explosions, where dying stars blast themselves apart with the force of billions of nuclear bombs. Over time, as the gas is consumed or expelled, star formation will decline, and the galaxy will age, gradually becoming more quiescent. The two supermassive black holes at the centers of the Milky Way and Andromeda will also eventually merge. As the galactic cores sink toward the center of the merged galaxy, the black holes will orbit each other, gradually spiraling inward due to the emission of gravitational waves. When they finally coalesce, they will form a single, even more massive black hole with a mass of over 100 million solar masses. This merger will release a tremendous amount of energy in the form of gravitational waves, though by the time these waves reach distant parts of the universe, they will be too weak to detect unless we have far more sensitive instruments than we do today. Computer simulations show exactly how we'll die. Thanks to modern supercomputers, astronomers have created detailed simulations of exactly what will happen when Andromeda and the Milky Way collide. These aren't just artists' impressions or vague predictions. Using the laws of gravity and the known masses, positions, and velocities of both galaxies, computers have calculated the collision second by second, star by star, over the next 10 billion years. And the results are spectacular, violent, and eerily beautiful. The simulations, run by teams at institutions like NASA's Goddard Space Flight Center and the Harvard-Smithsonian Center for Astrophysics, show that the collision will happen in stages, like a cosmic dance played out over billions of years. In about 3.75 billion years, Andromeda will loom enormous in our night sky, appearing several times larger than the full moon. At this point, the first close encounter will begin. The galaxies won't merge immediately, but will pass through each other like two swarms of bees, their stars never actually colliding because the distances between stars are so vast. But the gravitational forces will be catastrophic. Andromeda's gravity will stretch and distort the Milky Way, pulling out long tidal tails of stars that stream millions of light years into space. Our galaxy will do the same to Andromeda, ripping out streamers of stars and gas in elegant but violent arcs. The spiral structures of both galaxies will be destroyed in this first encounter, their beautiful arms torn apart and flung into space. After the first pass, the two galaxies will separate, moving apart for about 1 billion years, but gravity will pull them back together for a second collision, even more violent than the first. Computer simulations show that during this second encounter, the supermassive black holes at the centers of both galaxies will spiral toward each other, eventually merging in an event so energetic it will send ripples through the fabric of space-time itself, gravitational waves that could be detected by spacecraft billions of miles away. The simulations predict that after several close encounters spanning about 3 billion years, the two galaxies will finally merge completely, their stars mixed together in a chaotic cloud. Over time, this cloud will settle into a new structure, a giant elliptical galaxy that astronomers have already nicknamed Milkomeda. The beautiful spiral arms will be gone forever, replaced by a featureless egg-shaped distribution of stars. The vigorous star formation that characterizes spiral galaxies will cease, as much of the gas will have been consumed or ejected during the collisions. Milkomeda will be a galaxy of old, aging stars, a monument to the violent merger that created it. Most remarkably, the simulations show that despite the violence of the collision, individual stars will almost never actually hit each other. Space is simply too empty. Our Sun and solar system will be flung into a different orbit, possibly far from the galactic center, but the planets will remain intact. Life on Earth, if any still exists by then, will witness a night sky transformed beyond recognition, filled with strange new constellations and the brilliant glow of millions of new stars forming from compressed gas clouds. It will be the most dramatic cosmic event our neighborhood of the universe will experience for billions of years. The 140 million solar mass black hole devouring stars. At the center of the Andromeda Galaxy, hidden deep within the dense stellar bulge, lies a supermassive black hole. This black hole, with a mass between 100 and 230 million times that of the Sun, is one of the most massive black holes in the nearby universe, and is a defining feature of Andromeda's core. Understanding this black hole, its properties, and its influence on the surrounding galaxy is a key goal of modern astrophysics. Supermassive black holes are found at the centers of most large galaxies, and they play a crucial role in galactic evolution. They grow through the accretion of gas and through mergers with other black holes, and they can release tremendous amounts of energy as matter falls in, heating the surrounding gas and driving powerful winds and jets. This feedback can regulate star formation throughout the galaxy, making supermassive black holes far more than passive residents of galactic cores. The existence of Andromeda's central black hole was confirmed through observations of the motions of stars near the galactic center. By measuring the velocities of stars orbiting close to the center, astronomers can infer the mass of the central object. The stars are moving at speeds of hundreds of kilometers per second, and their orbits indicate the presence of an extremely massive, compact object that can only be a black hole. Observations with the Hubble Space Telescope and with ground-based telescopes equipped with adaptive optics, which corrects for atmospheric distortion, have provided detailed maps of the stellar motions near the center. One intriguing feature of Andromeda's core is that it appears to have a double nucleus, two concentrations of light separated by about 5 light-years. For many years, this was puzzling, leading to speculation that Andromeda might contain 2 supermassive black holes orbiting each other, perhaps the remnants of a past merger. However, more recent studies suggest a different explanation. The true center of the galaxy, where the black hole resides, is one of the bright peaks, while the other peak is a concentration of stars on eccentric orbits around the black hole. These stars form a lopsided disk, and when viewed from Earth, this disk creates the appearance of a double nucleus. The black hole at Andromeda's center is relatively quiescent, not actively accreting large amounts of matter. This is in contrast to active galactic nuclei, where supermassive black holes are consuming gas at high rates, producing intense radiation across the electromagnetic spectrum. Andromeda's black hole emits relatively weak radiation, detectable primarily in X-rays and radio waves, indicating that only small amounts of gas are falling in. This quiescence is typical of many nearby galaxies, including the Milky Way, where the central black hole is also relatively quiet. Despite its quiescence, Andromeda's black hole has likely played a significant role in the galaxy's history. During periods of active accretion, perhaps triggered by mergers or by the infall of gas clouds, the black hole would have released enormous amounts of energy, heating the surrounding gas and driving outflows. These feedback processes can suppress star formation in the central regions and shape the properties of the bulge. Evidence for past activity may be preserved in the structure of the bulge and in the distribution of gas and dust. The black hole also influences the dynamics of stars in the innermost regions of the galaxy. Stars on orbits that bring them too close to the black hole can be captured or disrupted. Tidal disruption events, where a star is torn apart by the black hole's tidal forces, are rare but spectacular, producing bright flares of radiation as the stellar debris is accreted. While no tidal disruption event has been observed in Andromeda, such events are observed in other galaxies and provide insights into the physics of accretion and the properties of black holes. In the future, when Andromeda and the Milky Way merge, their central black holes will eventually sink to the center of the merged galaxy and coalesce into a single, even more massive black hole. This merger will release gravitational waves, ripples in space-time that propagate at the speed of light. While the gravitational waves from such a distant event would be too weak to detect with current instruments, future space-based gravitational wave observatories like LISA, Laser Interferometer Space Antenna, may be able to detect similar events in other galaxies, providing a new way to study supermassive black holes and galaxy mergers. A mysterious ring of starbirth 75,000 light-years out. One of the strangest discoveries about Andromeda came in 2006 when NASA's Spitzer Space Telescope, observing in infrared light, revealed a massive ring of star formation located far outside the galaxy's visible disk. This ring, about 75,000 light-years from Andromeda's center, is invisible to optical telescopes because it's obscured by dust and contains mostly older stars. But in infrared wavelengths, it blazes with the heat signatures of dust, warmed by newborn stars. The ring itself is enormous, with a width of about 15,000 light-years, and it contains millions of solar masses of gas and dust. Most puzzling is its location, far beyond where most of Andromeda's stars reside, and in a region where the gas should be too sparse and diffuse to collapse and form stars. Yet here, somehow, stars are being born at a significant rate, adding to the mystery of what's driving this unexpected burst of star formation. Several theories have been proposed to explain the ring. One suggests that it formed from a head-on collision with another galaxy hundreds of millions of years ago. When two galaxies collide, the impact can send ripples of density waves propagating outward through the disk, like ripples on a pond. These density waves can compress gas at certain radii, triggering star formation in rings. The size and location of Andromeda's ring would be consistent with such a collision, though identifying the specific victim galaxy has proven difficult. Another possibility is that the ring formed from gas falling into Andromeda from the intergalactic medium, or from small satellite galaxies being torn apart by tidal forces. As this gas settles into orbit around Andromeda, it could accumulate at a specific radius determined by the balance between Andromeda's gravity and the angular momentum of the infalling material. This accumulated gas could then reach densities sufficient for star formation, creating the observed ring. What makes the ring especially intriguing is that it's not unique. Similar rings have been discovered around other galaxies, suggesting that this might be a common but previously overlooked feature of galactic structure. The Spitzer discovery of Andromeda's ring opened astronomers' eyes to a whole new component of galaxies that had been hiding in plain sight, invisible to conventional telescopes. It's a reminder that even objects we think we know well can surprise us when we look at them in new ways. The cannibal. Andromeda ate at least 2 galaxies already. Andromeda has a dark secret. It's a galactic cannibal that has devoured at least 2 smaller galaxies in its past, and the evidence of these ancient meals is written in the stars we see today. This discovery has transformed our understanding of how large galaxies like Andromeda grow and evolve, revealing a violent history hidden beneath its serene appearance. The evidence comes from detailed studies of the stars in Andromeda's outer regions and halo. Starting in the early 2000s, astronomers using large ground-based telescopes and the Hubble Space Telescope began to map the 3-dimensional distribution of stars around Andromeda with unprecedented precision. What they found was shocking. Clear streams and clumps of stars that don't fit the smooth distribution you'd expect in a galaxy's halo. These streams are the shredded remains of smaller galaxies that Andromeda has torn apart and consumed. One of the most prominent victims is a dwarf galaxy that astronomers estimate was consumed between 1 and 3 billion years ago. The remnants of this galaxy form a giant stellar stream that wraps around Andromeda like a ribbon, extending hundreds of thousands of light years into space. By tracing the orbit and composition of stars in this stream, astronomers have been able to reconstruct the death throes of the victim galaxy as it was pulled apart by Andromeda's immense gravity, its stars scattered like breadcrumbs along its orbital path. Another victim, consumed even more recently in galactic terms, has left its mark in a different way. Observations suggest that Andromeda's small companion galaxy M32, one of the brightest dwarf elliptical galaxies known, might actually be the dense core of a much larger galaxy that Andromeda is currently in the process of devouring. If this interpretation is correct, M32 is all that remains of a galaxy that was once comparable in size to the Milky Way, most of whose stars have already been stripped away and assimilated into Andromeda's halo. Studies of the chemical composition and ages of stars in Andromeda's halo have revealed that at least 2, and possibly more, major merger events have occurred in the galaxy's history. Each of these events added hundreds of billions of stars to Andromeda's population and triggered massive bursts of star formation as gas clouds collided and compressed. These ancient mergers shaped Andromeda into the massive galaxy we see today. This cannibalistic behavior isn't unique to Andromeda. Astronomers now believe that all large galaxies, including our own Milky Way, have grown primarily by consuming smaller neighbors. In fact, studies have shown that the Milky Way is in the process of devouring several small dwarf galaxies right now, including the Sagittarius dwarf elliptical galaxy, whose stars are being torn from it and scattered into long streams around our galaxy. The difference is that Andromeda, being larger and more massive, has been an even more voracious cannibal, eating more and larger victims than the Milky Way. This discovery has profound implications for understanding galaxy evolution. It means that the serene, orderly spiral structure we see in Andromeda is actually the result of a violent history of collisions and mergers. And it previews what will happen to the Milky Way when we collide with Andromeda in 4.5 billion years. We won't just merge with Andromeda, we'll be devoured by it, our stars scattered into streams, and eventually assimilated into the larger structure of Andromeda. The cannibal will claim another victim. Why does it spin the wrong way? One of the most bizarre and still unexplained features of Andromeda is the way some of its stars orbit the galaxy's center. Specifically, a significant population of stars in Andromeda's disk rotates in the opposite direction from the majority of the galaxy's stars, a phenomenon called retrograde motion. This is extremely unusual and suggests something dramatic happened in Andromeda's past. In most spiral galaxies, including our own Milky Way, the vast majority of stars orbit in the same direction, creating the smooth, coherent rotation that generates and maintains the spiral arm structure. This uniform rotation is a natural consequence of how galaxies form from rotating clouds of gas that collapse while conserving angular momentum. Everything should be spinning the same way, like water swirling down a drain. But in Andromeda, observations reveal a different story. Using spectroscopy to measure the velocities of thousands of stars across Andromeda's disk, astronomers discovered that a substantial population of stars, perhaps as much as 10 to 15% of the total, is moving in the wrong direction. These retrograde stars are distributed in a distinct disk structure, suggesting they're not just random interlopers, but form a coherent component of the galaxy. The discovery was made using observations from multiple telescopes, including the Keck Observatory in Hawaii and spectroscopic surveys that measured the Doppler shifts of starlight across Andromeda's disk. The data showed a clear bifurcation in the velocity distribution of stars. Most follow the expected rotation direction, but a significant minority move in the opposite sense. This was completely unexpected and has forced astronomers to rethink Andromeda's formation history. The most likely explanation is that the retrograde disk formed from a major merger event in Andromeda's past. If Andromeda collided with and absorbed another large galaxy that was orbiting in the opposite direction, the stars from that victim galaxy would have settled into a disk, rotating backward relative to Andromeda's original disk. Computer simulations of galaxy mergers show that such retrograde disks can indeed form and persist for billions of years, gradually mixing with the main disk but never fully losing their distinct kinematic signature. This retrograde population tells us that Andromeda's history was more violent than we might have guessed from its current appearance. The galaxy we see today is actually a composite structure built from the merger of multiple smaller galaxies, each contributing its own population of stars with different orbital characteristics. The existence of the retrograde disk is like a fossil record, preserving evidence of ancient collisions that shaped the galaxy billions of years ago. Interestingly, the Milky Way shows hints of similar retrograde populations in its own disk, though on a smaller scale. This suggests that the process of building large galaxies through mergers naturally creates these complex kinematic structures. When Andromeda and the Milky Way eventually merge, the resulting Andromeda will almost certainly have multiple populations of stars with different rotation patterns, creating an even more complex structure that will persist for billions of years, a permanent record of the violent collision that created it, the invisible dark matter cage holding it all together. Like all large galaxies, Andromeda is embedded in a massive halo of dark matter, an invisible component that dominates the galaxy's total mass and extends far beyond the visible stars and gas. Understanding the dark matter halo is crucial for understanding Andromeda's dynamics, its gravitational influence on satellites and neighboring galaxies, and the future collision with the Milky Way. Dark matter is one of the great mysteries of modern physics. We know it exists because of its gravitational effects, but we don't know what it's made of. It doesn't emit, absorb, or reflect light, making it invisible to all forms of electromagnetic radiation. The evidence for dark matter comes from observations of galactic rotation curves, the motions of galaxies in clusters, gravitational lensing, and the large-scale structure of the universe. In all cases, the gravitational effects indicate far more mass than can be accounted for by visible matter alone. In Andromeda, the presence of dark matter is inferred from the rotation curve, the relationship between orbital velocity and distance from the galactic center. In a galaxy with only visible matter, we would expect the orbital velocity to decrease with distance in the outer regions, following Kepler's laws. But observations show that the rotation curve remains flat or even rises slightly at large radii, indicating the presence of additional mass in the form of a dark matter halo. The dark matter halo of Andromeda is thought to extend hundreds of thousands of light-years from the galactic center, far beyond the visible disk and even beyond the stellar halo. Within this halo, the density of dark matter decreases with distance, following a profile that can be described by mathematical functions like the Navarro-Frank-White NFW profile, commonly used in cosmological simulations. The total mass of Andromeda, including dark matter, is estimated to be between 1 and 1.5 trillion solar masses, meaning it weighs 1.5 trillion times as much as our Sun, with dark matter making up the vast majority of this mass. The exact shape of the dark matter halo is still uncertain. It could be roughly spherical, as predicted by many simulations, or it could be somewhat flattened or elongated. Determining the shape requires detailed observations of the motions of stars and satellites in different parts of the halo and careful modeling of the gravitational potential. Recent studies using the orbits of Andromeda's satellite galaxies and stellar streams suggest that the halo may be slightly flattened, but the uncertainties are still large. One way to probe the dark matter halo is through the study of stellar streams, elongated structures of stars that trace the orbits of disrupted satellites. The shapes and properties of these streams depend on the gravitational potential through which they move, and by modeling the streams, astronomers can infer the distribution of dark matter. Several prominent streams have been identified in Andromeda's halo, and ongoing studies are using them to map the halo's structure. Another approach is to study the motions of Andromeda's satellite galaxies. These satellites are gravitationally bound to Andromeda and orbit within its dark matter halo. By measuring the velocities and positions of the satellites and modeling their orbits, astronomers can constrain the total mass of Andromeda and the shape of the halo. This method has the advantage of probing the halo at large distances from the galactic center, where the dark matter dominates. The nature of dark matter itself is still unknown, and Andromeda, like the Milky Way, provides a laboratory for testing dark matter theories. Leading candidates for dark matter particles include weakly interacting massive particles, WIMPs, axions, and sterile neutrinos. Each of these candidates has different properties and would produce different distributions of dark matter in galaxies. By comparing observations of Andromeda's halo to predictions from simulations with different dark matter models, astronomers can constrain the properties of dark matter and potentially rule out some candidates. One puzzle is the distribution of dark matter on small scales. Simulations predict that dark matter halos should contain numerous subhalos, smaller concentrations of dark matter left over from the hierarchical assembly of the galaxy. Some of these subhalos might host dwarf satellite galaxies, but many should be dark, containing no stars at all. The number and properties of these subhalos depend on the nature of dark matter, and observations of Andromeda's satellites and stellar streams can provide tests of these predictions. The dark matter halo also plays a crucial role in the future collision between Andromeda and the Milky Way. The halos of the two galaxies will interact and merge, and the distribution of dark matter will influence the dynamics of the collision, the formation of tidal tails, and the final structure of the merged galaxy. Simulations of the collision take into account not just the visible stars and gas, but also the dark matter, and they predict how the halos will evolve and eventually settle into a single, larger halo. Hubble's billion-pixel image that revealed 100 million stars. Our understanding of Andromeda has advanced dramatically thanks to increasingly sophisticated telescopes and instruments. The Hubble Space Telescope, launched in 1990 and still operational today, has been instrumental in studying Andromeda in unprecedented detail. In 2012, astronomers using Hubble created the largest and sharpest image ever taken of Andromeda, a mosaic composed of 7,398 individual exposures taken over 411 pointings of the telescope. The resulting image contained over 1.5 billion pixels and revealed more than 100 million stars in a 61,000 light-year-long section of the galaxy. This Hubble image, which would require 600 HD television screens to display at full resolution, allowed astronomers to study individual stars in Andromeda for the first time, measuring their brightnesses, colors, and ages. They discovered that the galaxy's disk contains stars of all ages, from ancient stars formed over 10 billion years ago to young, hot blue stars just a few million years old. The image also revealed thousands of star clusters, hundreds of dense stellar associations, and intricate structures in the dust lanes that wind through the spiral arms. The Spitzer Space Telescope, which observed in infrared wavelengths from 2003 to 2020, revealed a different view of Andromeda. Infrared light can penetrate the dust that obscures visible light, allowing Spitzer to see star-forming regions hidden from optical telescopes. Spitzer's observations showed that Andromeda has a massive ring of star formation located 75,000 light-years from its center, far outside the visible disk. This ring contains millions of solar masses of dust and gas and is birthing new stars at a prodigious rate. Andromeda has been one of the most intensively studied objects in astronomy, and over the decades, astronomers have used a wide variety of techniques and instruments to observe it. These observations span the electromagnetic spectrum, from radio waves to gamma rays, and they have revealed the galaxy's structure, composition, and dynamics in exquisite detail. In visible light, Andromeda is a spectacular sight through even modest telescopes. Its central bulge and the inner parts of its disk are bright and can be seen with binoculars or a small telescope, while larger telescopes reveal the spiral arms, dust lanes, and star-forming region. Long-exposure photographs taken with professional telescopes show the full extent of Andromeda, including faint outer regions and stellar streams in the halo. One of the most important observations of Andromeda in recent decades came from the Hubble Space Telescope, which has taken numerous images of different regions of the galaxy. Hubble's resolution, free from the blurring effects of Earth's atmosphere, allows it to resolve individual stars within Andromeda, even though the galaxy is 2.5 million light-years away. By imaging millions of stars and measuring their brightnesses and colors, astronomers can determine their ages, temperatures, and compositions, providing a detailed census of Andromeda's stellar populations. The X-ray mystery. Hundreds of phantom sources. When astronomers pointed NASA's Chandra X-ray Observatory at Andromeda, they expected to find a handful of X-ray sources, perhaps a few dozen, mostly from binary star systems where a neutron star or black hole is devouring a companion star. What they actually found was far more mysterious and exciting. Chandra detected over 150 distinct X-ray sources scattered throughout Andromeda, and many of them remain unexplained to this day. X-rays are produced by some of the most extreme and violent processes in the universe. Matter falling onto black holes or neutron stars, supernova remnants still glowing from their explosive origins, superhot gas heated to millions of degrees by shock waves, and the violent interaction of stellar winds from massive stars. Finding X-ray sources in a galaxy tells us where the most energetic and dramatic events are occurring. Some of Andromeda's X-ray sources are relatively easy to identify. About 40% of them appear to be X-ray binaries, systems where a compact object, like a neutron star or black hole, is pulling matter from a normal companion star. As this material spirals onto the compact object, it heats up to tens of millions of degrees, hot enough to emit X-rays. We know these are binaries because their X-ray brightness varies periodically as the two stars orbit each other, and because they're associated with optical counterparts that show the characteristic signatures of binary systems. Another identifiable population consists of supernova remnants, the expanding shells of debris left behind when massive stars explode. These remnants can emit X-rays for thousands of years after the explosion as the shock wave plows through surrounding gas, heating it to extreme temperatures. Chandra has identified about 15 confirmed supernova remnants in Andromeda, each representing a star that died in the relatively recent past. But here's where it gets mysterious. More than half of the X-ray sources Chandra detected don't fit neatly into any known category. They're not obviously binaries because they don't show the expected periodic variations. They're not associated with supernova remnants or known clusters of hot stars. They're simply isolated points of X-ray emission with no clear optical counterpart and no obvious explanation for why they're producing X-rays. Several possibilities have been proposed for these phantom sources. Some could be background objects, galaxies or quasars billions of light years behind Andromeda that happen to lie along our line of sight. But statistical analysis suggests that many of them are truly part of Andromeda, embedded within the galaxy, but defying easy explanation. They could be unusual types of binary systems we haven't encountered before, perhaps involving unusual combinations of stellar remnants or very low-mass companions that are difficult to detect optically. Another intriguing possibility is that some of these sources are intermediate-mass black holes, objects with masses between 100 and 100,000 times the Sun's mass. These would be larger than the stellar mass black holes formed from single massive stars, but smaller than the supermassive black holes found at galaxy centers. Intermediate mass black holes are predicted by theory, but have proven maddeningly difficult to confirm observationally. If some of Andromeda's mysterious X-ray sources turn out to be intermediate mass black holes, it would be a major discovery with implications for understanding how supermassive black holes form and grow. The James Webb Space Telescope and future X-ray observatories are expected to help solve the mystery of these phantom sources by providing more detailed observations in multiple wavelengths. But for now, they remain one of Andromeda's most tantalizing mysteries, a reminder that even in our nearest major galactic neighbor, there are still phenomena we don't understand, and discoveries waiting to be made. Every X-ray photon that Chandra detects from these mysterious sources is a clue in a cosmic detective story we're still working to solve. Earth survives, but our night sky will never be the same. The future collision and merger of Andromeda and the Milky Way is one of the most dramatic events that will occur in our region of the universe. While it is still billions of years away, astronomers have used simulations to predict what will happen, and the results are both spectacular and scientifically fascinating. The merged galaxy, often called Milkomeda or Milkdromeda, will be a completely different type of galaxy from its progenitors, and understanding this transformation provides insights into galaxy evolution across cosmic time. The collision will begin in about 3.75 to 4 billion years, when Andromeda and the Milky Way make their first close passage. At this point, Andromeda will dominate the night sky, appearing many times larger than the full moon. The two galaxies will pass through or near each other, and tidal forces will begin to distort their structures. Long streamers of stars, gas, and dark matter will be pulled out from both galaxies, creating spectacular tidal tails that extend for hundreds of thousands of light years. During this first passage, the galaxies will not merge immediately, but will swing around each other, their mutual gravity pulling them back for additional encounters. With each passage, the galaxies lose energy through tidal interactions and the dynamical friction of dark matter and stars moving through each other. The orbits decay, and the galaxies draw closer together. Simulations suggest there will be 2 or 3 close passages before the final merger, spread over a period of about 2 to 3 billion years after the first encounter. As the galaxies collide, gas clouds will ram into each other, compressing and heating the gas. This compression will trigger intense bursts of star formation, creating a starburst phase with star formation rates potentially 100 times higher than today. Massive star clusters and brilliant HI regions will form throughout the colliding regions, lighting up the galaxy with the blue and ultraviolet light of young hot stars. The night sky, as seen from Earth, if Earth is still intact and habitable, will be ablaze with new stars and glowing nebulae. The collision will also disrupt the ordered rotation of the 2 disks. As stars interact gravitationally, their orbits become more random, and the disk structures are gradually destroyed. The spiral arms will be erased, and the flat, rotating disks will puff up into a more spheroidal shape. The final product will be a large elliptical galaxy, with stars moving on a variety of orbital paths, rather than in the organized patterns of a disk. Elliptical galaxies lack the prominent disks and spiral structures of spirals and are dominated by older, redder stars. The total mass of Milkomeda, including stars, gas, and dark matter, will be about 2 to 3 trillion solar masses, making it one of the largest galaxies in the local group. The merger will also involve the satellite galaxies of both the Milky Way and Andromeda. Some satellites will be ejected into intergalactic space during the collision, while others will fall into the merged galaxy and be disrupted, adding their stars to the mix. At the center of the merged galaxy, the 2 supermassive black holes will eventually coalesce. As the galactic cores sink towards the center, the black holes will form a binary system, orbiting each other while gradually spiraling inward due to the emission of gravitational waves. When they finally merge, they will create a single black hole with a mass of over 100 million solar masses. This merger will release a tremendous burst of gravitational wave energy, though it will be far too distant for us to detect with current technology. After the merger is complete and the galaxy settles into its final form, star formation will decline. The intense starburst phase will consume or expel much of the gas, leaving little fuel for new stars. Milkomeda will gradually age, with the stellar population becoming older and redder as massive stars die and no new stars are born to replace them. Over tens of billions of years, the galaxy will become increasingly quiescent, a relic of the violent merger that created it. The fate of our solar system during this merger is uncertain. Direct collisions between stars are extremely rare because the distances between stars are so vast. The Sun and its planets will likely survive the merger physically intact, but they may be flung into a very different orbit. Simulations suggest several possible outcomes. The solar system could end up in the central regions of Milkomeda, in the outer halo, or even ejected into intergalactic space. If ejected, the night sky would become dark, with few stars visible, as the solar system drifts through the emptiness between galaxies. However, it's important to note that in 4 to 5 billion years, the Sun will be nearing the end of its main sequence lifetime. It will have become significantly brighter and hotter, and Earth's oceans may have evaporated, making the planet uninhabitable long before the merger. So while the collision is a fascinating event to consider, life on Earth, if it still exists, will likely face more immediate challenges from the Sun's evolution than from the galactic collision. Milkomeda, the giant elliptical graveyard, will become. The future collision and merger of Andromeda and the Milky Way is one of the most dramatic events that will occur in our region of the universe. While it is still billions of years away, astronomers have used simulations to predict what will happen, and the results are both spectacular and scientifically fascinating. The merged galaxy, often called Milkomeda or Milkdromeda, will be a completely different type of galaxy from its progenitors, And understanding this transformation provides insights into galaxy evolution across cosmic time. The collision will begin in about 3.75 to 4 billion years, when Andromeda and the Milky Way make their first close passage. At this point, Andromeda will dominate the night sky, appearing many times larger than the full moon. The two galaxies will pass through or near each other, and tidal forces will begin to distort their structures. Long streamers of stars, gas, and dark matter will be pulled out from both galaxies, creating spectacular tidal tails that extend for hundreds of thousands of light years. During this first passage, the galaxies will not merge immediately, but will swing around each other, their mutual gravity pulling them back for additional encounters. With each passage, the galaxies lose energy through tidal interactions and the dynamical friction of dark matter and stars moving through each other. The orbits decay and the galaxies draw closer together. Simulations suggest there will be 2 or 3 close passages before the final merger, spread over a period of about 2 to 3 billion years after the first encounter. As the galaxies collide, gas clouds will ram into each other, compressing and heating the gas. This compression will trigger intense bursts of star formation, creating a starburst phase with star formation rates potentially 100 times higher than today. Massive star clusters and brilliant HII regions will form throughout the colliding regions, lighting up the galaxy with the blue and ultraviolet light of young, hot stars. The night sky, as seen from Earth, if Earth is still intact and habitable, will be ablaze with new stars and glowing nebulae. The collision will also disrupt the ordered rotation of the two disks. As stars interact gravitationally, their orbits become more random, and the disk structures are gradually destroyed. The spiral arms will be erased, and the flat, rotating disks will puff up into a more spheroidal shape. The final product will be a large elliptical galaxy, with stars moving on a variety of orbital paths rather than in the organized patterns of a disk. Elliptical galaxies lack the prominent disks and spiral structures of spirals and are dominated by older, redder stars. The total mass of Milkomeda, including stars, gas, and dark matter, will be about 2 to 3 trillion solar masses, making it one of the largest galaxies in the local group. The merger will also involve the satellite galaxies of both the Milky Way and Andromeda. Some satellites will be ejected into intergalactic space during the collision, while others will fall into the merged galaxy and be disrupted, adding their stars to the mix. At the center of the merged galaxy, the two supermassive black holes will eventually coalesce. As the galactic cores sink toward the center, the black holes will form a binary system orbiting each other while gradually spiraling inward due to the emission of gravitational waves. When they finally merge, they will create a single black hole with a mass of over 100 million solar masses. This merger will release a tremendous burst of gravitational wave energy, though it will be far too distant for us to detect with current technology. After the merger is complete and the galaxy settles into its final form, star formation will decline. The intense starburst phase will consume or expel much of the gas, leaving little fuel for new stars. Milkomeda will gradually age, with the stellar population becoming older and redder as massive stars die and no new stars are born to replace them. Over tens of billions of years, the galaxy will become increasingly quiescent, a relic of the violent merger that created it. The fate of our solar system during this merger is uncertain. Direct collisions between stars are extremely rare because the distances between stars are so vast. The Sun and its planets will likely survive the merger physically intact, but they may be flung into a very different orbit. Simulations suggest several possible outcomes. The solar system could end up in the central regions of Milkomeda, in the outer halo, or even ejected into intergalactic space. If ejected, the night sky would become dark, with few stars visible, as the solar system drifts through the emptiness between galaxies. However, it's important to note that in 4 to 5 billion years, the Sun will be nearing the end of its main sequence lifetime. It will have become significantly brighter and hotter, and Earth's oceans may have evaporated, making the planet uninhabitable long before the merger. So while the collision is a fascinating event to consider, life on Earth, if it still exists, will likely face more immediate challenges from the Sun's evolution than from the galactic collision. What Andromeda teaches us about our cosmic fate. Beyond the scientific details, the Andromeda Galaxy holds a special place in human culture and imagination. It is one of the few deep sky objects visible to the naked eye, a faint smudge of light that has been observed by humans for millennia. This connection between Andromeda and humanity, spanning cultures and epochs, gives the galaxy a significance that goes beyond its astronomical properties. For ancient observers, Andromeda was a mystery. Without telescopes, they could only see a faint, cloudy patch, different from the sharp points of stars. Different cultures interpreted this object in various ways. In Greek mythology, the constellation Andromeda is named after the princess Andromeda, who was chained to a rock as a sacrifice to a sea monster, but was rescued by the hero Perseus. The fuzzy patch we now know as the Andromeda Galaxy was noted within this constellation, though its true nature was unknown. Islamic astronomers in the medieval period, including Abd al-Rahman al-Sufi, documented the little cloud in the constellation Andromeda, providing some of the earliest written records of the object. These observations were part of a broader tradition of careful sky observation and catalogue making that preserved and extended Greek astronomical knowledge and influenced later European astronomy. When telescopes were invented, Andromeda became a subject of intense interest. Early telescopic observers could see that it was not a simple point of light, but an extended, nebulous object with structure. This led to debates about its nature. Was it a cloud of gas within our own stellar system, or was it something more distant and grand? The question remained unanswered for centuries, fueling speculation and wonder. The resolution of this question in the 1,920 seconds, when Hubble proved that Andromeda was a separate galaxy, was a turning point not just in astronomy, but in human thought. The realization that the universe contained billions of galaxies, each potentially containing billions of stars, and perhaps countless planets, expanded the scope of human imagination and raised profound questions about our place in the cosmos. If the universe is so vast, with so many stars and galaxies, what is the likelihood that life exists elsewhere? Are we alone, or are there other civilizations looking up at their own night skies and wondering the same questions? Andromeda has also inspired artists, writers, and philosophers. Its image, captured in photographs and paintings, evokes a sense of beauty and wonder. Science fiction writers have imagined journeys to Andromeda, encounters with alien civilizations, and adventures in a galaxy far from our own. While we know that traveling to Andromeda is far beyond our current or foreseeable technological capabilities, the galaxy serves as a symbol of the unknown, the exotic, and the possible. The future collision between Andromeda and the Milky Way has also captured popular imagination. The idea that our galaxy is on a collision course with another galaxy, and that this collision will dramatically transform our cosmic neighborhood, is both thrilling and humbling. It reminds us that even on cosmic scales, change is inevitable, and that the universe is a dynamic, evolving place. The collision also provides a tangible connection to the distant future, a way of thinking about timescales far beyond human lifetimes and imagining what the cosmos will be like billions of years from now. For many people, Andromeda is a gateway to astronomy and to a deeper appreciation of the universe. Seeing the galaxy through a telescope, or even with the naked eye on a dark night, can be a transformative experience. It brings home the reality of the cosmos, the fact that there are other galaxies out there, immensely distant yet visible, composed of billions of stars just like our own Sunday. This direct, personal connection to the universe is one of the most powerful aspects of astronomy, making the abstract concrete and the distant near. Andromeda also serves as a reminder of the importance of preserving dark skies. Light pollution from cities and towns obscures the night sky, making it difficult or impossible to see faint objects like Andromeda. As more people live in urban areas, and as artificial lighting becomes more widespread, the experience of seeing the natural night sky is becoming rarer. Efforts to reduce light pollution and to create dark sky reserves help ensure that future generations can experience the wonder of seeing Andromeda and other celestial objects with their own eyes, maintaining a connection to the cosmos that humans have enjoyed for thousands of years. The study of Andromeda is also a collaborative, international endeavor. Astronomers from around the world, working with telescopes on multiple continents and in space, contribute to our understanding of the galaxy. Data is shared, papers are published in international journals, and conferences bring together researchers to discuss their findings. This collaboration transcends national boundaries and political divisions, united by a common goal to understand the universe. Andromeda, in this sense, is a symbol of the best of human cooperation and curiosity. Finally, Andromeda reminds us of the deep connections between science and society. The technologies developed for observing Andromeda, from adaptive optics to space telescopes to sophisticated detectors, often find applications in other fields, from medicine to communications to computing. The questions raised by studying Andromeda about the nature of matter, the structure of the universe, and the origins of life are among the most profound that humans can ask. Investing in the study of Andromeda and other cosmic objects is an investment in knowledge, in technology, and in the human spirit of exploration and discovery. Viewing Andromeda from Earth. A personal experience. If you've never seen Andromeda with your own eyes, you're missing one of the most profound experiences amateur astronomy can offer. Unlike most deep sky objects that require telescopes to appreciate, Andromeda is visible to the naked eye from any reasonably dark location. All you need is a clear autumn or winter evening, away from city lights, and the knowledge of where to look. The best time to observe Andromeda from the northern hemisphere is during the fall and winter months, from September through February, when the constellation Andromeda rides high in the evening sky. To find it, first locate the Great Square of Pegasus, 4 bright stars forming a large square in the southern sky. From the northeastern corner of the square, follow a line of stars curving to the northeast. This is the constellation Andromeda, and about 2/3 of the way along this chain, you'll find M31, the Andromeda Galaxy, appearing as a small, fuzzy oval patch of light. To the naked eye, Andromeda appears as a faint, elongated smudge, like a cotton ball stretched out lengthwise. It's not an overwhelmingly obvious sight. You might initially mistake it for a small cloud or dismiss it as nothing special. But when you realize what you're looking at, the impact is profound. Those photons hitting your retina have been traveling through space for 2.5 million years. They left Andromeda when our human ancestors in Africa were just beginning to use stone tools, long before anatomically modern humans evolved, before language, before civilization. You're seeing across an abyss of time and space that defies human comprehension. With binoculars, Andromeda reveals more of its structure. A good pair of 10x50 binoculars will show the galaxy's elongated shape more clearly, and you might catch hints of the dust lanes that cross the spiral arms. The view is stunning in its simplicity, a glowing ellipse floating against the star-studded background of the Milky Way. If you have access to a small telescope, even a modest 3 or 4 inch instrument will show Andromeda's bright nucleus and the fainter outer regions. Larger telescopes, 8 inches or more in aperture, can reveal the spiral arms and dark dust lanes, though the galaxy's sheer size means you'll need to scan across it to take in all the details. Astrophotographers have captured breathtaking images of Andromeda using modern digital cameras and tracking mounts. With exposures lasting hours and sophisticated processing techniques, these images reveal details invisible to the eye. The intricate structure of the spiral arms, the delicate dust lanes, the blue glow of young star clusters, the reddish emission from hydrogen gas in star-forming regions, and even some of the larger globular clusters surrounding the galaxy. Many amateur astronomers have produced images of Andromeda that rival professional observations from just a few decades ago, a testament to the revolution in imaging technology. But even without any equipment, just seeing Andromeda with your naked eye connects you to the cosmos in a visceral way. You're not looking at a photograph or an artist's conception. You're seeing it right now, in real time, accounting for the 2.5 million year light travel time. You're participating in an act of observation that humans have been performing for thousands of years, from the Persian astronomer Abd al-Rahman al-Sufi in 964 AD, who called it a little cloud, to Charles Messier in 1764, to Edwin Hubble in the 1920 seconds, to countless amateur and professional astronomers today. Every photon you detect is a messenger from another galaxy, carrying information about stars and gas and dust unimaginably far away, and your eye is the destination of a journey that began when our ancestors were learning to control fire. The Great Debate and Hubble's breakthrough, the story of how we came to understand Andromeda's true nature, is one of the most dramatic in the history of astronomy, culminating in a discovery that literally expanded our conception of the universe overnight. For centuries, Andromeda was simply another celestial curiosity, a fuzzy patch catalogued by astronomers but not understood. The invention of the telescope revealed more detail but also deepened the mystery. Was it a nearby cloud of gas within our Milky Way, or something else entirely? By the early 20th century, telescopes had improved enough that astronomers could see spiral structure in many nebulae, including Andromeda. Some astronomers, noting the resemblance to theoretical models of solar systems forming, proposed that these spiral nebulae were nascent solar systems within our galaxy, planetary systems in the process of forming around new stars. Others suspected they might be distant galaxies in their own right, island universes, comparable to the Milky Way, but separated from us by unimaginable distances. This question became the subject of the Great Debate, a famous discussion held on the 26th of April 1920 at the National Academy of Sciences in Washington, D.C., between astronomers Harlow Shapley and Heber Curtis. Shapley argued that spiral nebulae were part of the Milky Way, which he proposed was a vast system hundreds of thousands of light years across, making it essentially the entire universe. Curtis contended that spiral nebulae were separate galaxies outside the Milky Way, which he argued was much smaller, and that the universe contained countless such galaxies. The debate was inconclusive, largely because the observational evidence available at the time was ambiguous. What was needed was a reliable way to measure the distances to spiral nebulae. If they were nearby, Shapley was right. If they were millions of light years away, Curtis was vindicated. The problem was that there was no known method that could accurately measure such vast distances. That changed with Edwin Hubble's observations in the 1920 seconds. Hubble, working at the Mount Wilson Observatory in California with the 100-inch Hooker telescope, the largest telescope in the world at the time, focused his attention on Andromeda. In 1923, he discovered what he was looking for: a Cepheid variable star in the outer regions of Andromeda. Cepheid variables are special stars whose brightness pulsates regularly, and, crucially, the period of pulsation is directly related to the star's intrinsic luminosity. By measuring the period, astronomers can determine how bright the star truly is, and by comparing that to how bright it appears, they can calculate the distance. Hubble's Cepheid variable had a period that indicated it was extremely luminous, but it appeared faint in his photographs. The mathematics were unambiguous. To appear so faint, despite being so intrinsically bright, the star must be incredibly distant. Hubble calculated that Andromeda was roughly 900,000 light-years away, far beyond any conceivable boundary of the Milky Way. Later, refinements would revise this distance upward to the currently accepted value of about 2.5 million light-years. But even Hubble's initial estimate was revolutionary. It meant that Andromeda was a separate galaxy, an island universe in its own right, and if one spiral nebula was a galaxy, then they probably all were. The universe was vastly larger than anyone had imagined. Hubble announced his discovery in 1924, and it sent shockwaves through the astronomical community. Overnight, the scale of the known universe expanded by orders of magnitude. The Milky Way was not the entirety of creation, but merely one galaxy among countless others. This was a Copernican revolution in scope, comparable to the realization centuries earlier that Earth was not the center of the solar system. Once again, humanity's place in the cosmos had been diminished, and once again, the universe had revealed itself to be far grander and more magnificent than we had dared to imagine. And it all began with a single star, a Cepheid variable in the outskirts of Andromeda, whose rhythmic pulsations held the key to unlocking the true scale of the universe. The aftermath. What happens to Earth and our solar system? One of the first questions people ask when they learn about the Andromeda collision is, will Earth be destroyed? The short answer is, no, probably not. But the long answer is far more interesting, and involves understanding just how empty space really is, and how gravity works on cosmic scales. Despite the violence of the galaxy collision, individual stars almost never actually collide with each other. This seems counterintuitive when you consider that we're talking about two galaxies, each containing hundreds of billions of stars, smashing together. Surely some stars must hit each other. But space is so incomprehensibly vast and empty that even during a galactic collision, the distances between stars are so large that actual stellar collisions are extraordinarily rare. To understand why, consider the scale. The Sun is about 865,000 miles in diameter, but the nearest star, Proxima Centauri, is about 25 trillion miles away. If you scaled the Sun down to the size of a grain of sand, Proxima Centauri would be another grain of sand about 4 miles away. Now imagine 2 beaches worth of sand grains passing through each other. Even though there are billions of grains, the chances of any two actually colliding are vanishingly small. That's what happens when galaxies collide. However, just because stars don't collide doesn't mean they're unaffected. The gravitational interactions during the merger will dramatically alter stellar orbits. Computer simulations show that our Sun, currently residing in a fairly circular orbit about 26,000 light-years from the Milky Way's center, will be flung into a wildly different orbit during the collision. We might end up much closer to the center of Milkomeda, surrounded by a far denser concentration of stars, or we might be ejected to the distant outskirts, billions of light-years from the galactic core, in a sparse region of space with few nearby stars. The planets, though, will almost certainly remain bound to the Sunday. The distances between planets are tiny compared to interstellar distances, and the Sun's gravity is strong enough to hold onto its planetary system even as the galaxy is torn apart around it. Earth, Mars, Jupiter, and the rest will continue their orbital dance around the Sun, apparently unaware of the cosmic catastrophe unfolding on larger scales. From Earth's surface, the collision will be spectacular but not immediately dangerous. The night sky will be transformed as Andromeda looms larger and larger, eventually dominating the view. At closest approach, Andromeda will appear 10 times larger than the full moon, a magnificent spiral filling a huge swath of sky. As the galaxies tear through each other, the sky will be alive with new stars. The collision will compress vast clouds of gas triggering intense bursts of star formation. Millions of massive, hot blue stars will be born, blazing brilliantly for a few million years before exploding as supernovae. The night sky on Earth will be lit by these brilliant new stars, and on any given night, observers might see dozens of supernovae scattered across the heavens, some bright enough to cast shadows. It will be the greatest cosmic fireworks display in billions of years, visible for millions of years as the galaxies merge and settle. There is, however, one potentially serious threat: the supermassive black holes at the centers of both galaxies. As Andromeda and the Milky Way merge, their central black holes will spiral toward each other, eventually merging in a catastrophic event. This merger will release an enormous burst of energy, possibly including jets of radiation and particles that could, in principle, sterilize planets unlucky enough to be in their path. The good news is that the solar system's location in the outer parts of the Milky Way makes it unlikely we'll be in the danger zone. The bad news is that we can't be entirely certain where we'll be by the time the black holes merge, given the chaotic rearrangement of stellar orbits during the collision. But here's the thing: none of this will matter to humanity as we currently exist. The collision won't even begin for another 3.75 billion years. Earth itself has only existed for about 4.5 billion years, meaning the collision is as far in our future as the formation of Earth is in our past. By the time Andromeda arrives, Earth will be a vastly different place, if it even still exists in a habitable form. The Sun, currently a stable middle-aged star, will have brightened significantly as it ages, making Earth progressively hotter. Within 1 billion years, the oceans will have evaporated. Within 3 billion years, Earth will likely be a scorched, lifeless rock. Any descendants of humanity that still exist when Andromeda collides will be living elsewhere, perhaps on terraformed worlds in the outer solar system, perhaps in space habitats, perhaps among the stars themselves. They will witness the collision from perspectives we can scarcely imagine, but one thing is certain: it will be a sight unlike any ever seen. The future of star formation in Milkomeda. One of the most profound consequences of the Andromeda-Milky Way merger is that it will effectively end star formation in our region of the universe. The beautiful, vigorous spiral galaxies we see today, with their bright blue spiral arms lit by massive young stars, will be replaced by a giant elliptical galaxy where new star formation has essentially ceased. Understanding why requires understanding how star formation works in spiral galaxies and what changes when they merge. In a spiral galaxy like Andromeda or the Milky Way, star formation occurs primarily in the spiral arms, where density waves compress gas clouds as they pass through. These compressed regions become gravitationally unstable and collapse to form new stars. The process is ongoing and efficient, with the gas supply replenished by material falling in from the halo and by the death of existing stars, which return much of their mass to the interstellar medium. In the Milky Way, about 1 to 3 new stars form every year, maintaining a healthy population of young, bright stars that give the galaxy its characteristic blue-white glow. Elliptical galaxies are different. They lack the organized rotation and spiral structure of disk galaxies, instead containing stars moving in random orbits in a 3-dimensional ellipsoidal distribution. More importantly, they contain very little gas and dust, the raw materials needed for star formation. Observations of elliptical galaxies throughout the universe show that they're dominated by old, red stars, with little to no ongoing star formation. They're stellar graveyards, beautiful in their own way, but lacking the vigor and vitality of spiral galaxies. When 2 spiral galaxies collide and merge, the result is typically an elliptical galaxy. The collision disrupts the delicate structure needed for efficient star formation. The orderly rotation of the disks is destroyed, the spiral arms are torn apart, and much of the gas is either consumed in a final burst of star formation during the collision, or is ejected from the galaxy entirely by the violence of the interaction. Computer simulations show that the merger of Andromeda and the Milky Way will follow this pattern. During the collision phases, there will be intense star formation as gas clouds collide and compress. Millions of massive stars will form, blazing brilliantly but briefly. But once the merger is complete and Milkomeda has settled into its new configuration, very little gas will remain, and star formation will drop to a trickle. The last stars to form in Milkomeda will be the most important in a sense. Red dwarfs, stars with masses less than about half the Sun's, burn their fuel so slowly that they can shine for trillions of years, far longer than the current age of the universe. The red dwarfs forming during the final stages of star formation in Milkomeda will still be shining long after the Sun and all current stars have died, the last embers of a once vigorous galaxy. Over the coming trillions of years, as these red dwarfs slowly exhaust their fuel and fade away, Milkomeda will grow progressively darker and deader, a galaxy of increasingly dim stellar remnants, white dwarfs, neutron stars, and black holes orbiting in the dark. This fate isn't unique to Milkomeda. Astronomers observing the universe see that most star formation occurred billions of years ago, when the universe was younger and gas was more abundant. The rate of star formation in the universe has been declining for billions of years and will continue to decline. Mergers like the one between Andromeda and the Milky Way represent the endgame of galaxy evolution, the transformation of gas-rich spirals into gas-poor ellipticals. It's a cosmic autumn, a slow winding down as the universe uses up its resources and settles into a state of increasing entropy. But there's a silver lining, if you can call it that. The massive burst of star formation during the Andromeda-Milky Way collision will produce millions of stars that wouldn't have formed otherwise. In a sense, the merger accelerates star formation in the short term, even as it dooms it in the long term. Many of these stars will have planetary systems, and on some of those planets, conditions might be right for life. The collision will create opportunities, even as it forecloses others. It's the ultimate example of creation through destruction, death, and rebirth playing out on a galactic scale. Andromeda dominates the local group of 80 galaxies. Understanding Andromeda means understanding its role in the local group, the small cluster of galaxies that includes the Milky Way, Andromeda, and about 80 smaller dwarf galaxies. The local group is our cosmic neighborhood, the framework within which we understand the gravitational interactions, star formation histories, and ultimate fates of all its member galaxies. The local group is about 10 million light-years in diameter, and its structure is dominated by two massive galaxies, Andromeda and the Milky Way. Together, these two galaxies contain the vast majority of the mass and stars in the local group. The third largest member is the Triangulum Galaxy, also known as M33, a small spiral galaxy with a mass only about 5% that of the Milky Way. Beyond these three, the local group contains dozens of dwarf galaxies, small systems ranging from a few million to a few billion stars. The dwarf galaxies are clustered around Andromeda and the Milky Way, orbiting the two giants like moons around planets. Andromeda has at least 14 confirmed satellite galaxies, including M32 and M110, two bright dwarf ellipticals visible through small telescopes. The Milky Way has a similar retinue, including the Large and Small Magellanic Clouds, visible to the naked eye from the southern hemisphere, and numerous smaller dwarfs discovered in recent years by surveys like the Sloan Digital Sky Survey. These satellite galaxies are not just passive companions. They interact gravitationally with their host galaxies, and many are in the process of being tidally disrupted and consumed. We've already discussed how Andromeda has devoured several small galaxies in the past, and the same is true for the Milky Way. The Sagittarius dwarf elliptical galaxy, for example, is currently being torn apart by the Milky Way's gravity, its stars scattered into long streams that wrap around our galaxy. This process of accretion is how large galaxies grow, cannibalizing their smaller neighbors and adding their stars to the halo. The local group is gravitationally bound, meaning its member galaxies are held together by mutual gravity and are not participating in the overall expansion of the universe that carries more distant galaxies away from us. In fact, the local group is slowly contracting, with Andromeda and the Milky Way dominating the dynamics and drawing the smaller galaxies toward them. When Andromeda and the Milky Way merge, Milkomeda will become the undisputed ruler of the local group, with all the dwarf galaxies either already consumed or orbiting the merged system. Beyond the local group, the nearest large concentration of galaxies is the Virgo cluster, about 50 to 60 million light-years away. The Virgo cluster contains over 1,500 galaxies, including the giant elliptical galaxy M87, which has a mass tens of times greater than Andromeda or the Milky Way. The local group is actually on the outskirts of the Virgo supercluster, a larger structure containing multiple galaxy clusters and groups. On even larger scales, the Virgo supercluster is part of the Laniakea supercluster, a vast structure containing over 100,000 galaxies and spanning 500 million light-years. Andromeda's place in this hierarchy is that of a major galaxy in a small, relatively isolated group. If the local group were located in a denser environment like the Virgo cluster, the history would have been very different. In dense clusters, galaxy collisions and mergers happen frequently, and the environment is harsh, with hot intra-cluster gas stripping cold gas from galaxies and quenching star formation. Many cluster galaxies have already merged to form giant ellipticals, and the future holds more mergers and interactions. In contrast, the local group's relative isolation has allowed Andromeda and the Milky Way to evolve more peacefully, retaining their spiral structures until now. The upcoming merger is, in a sense, the local group's coming of age, the transition from a phase of isolated growth to a phase of violent interaction, the human significance, why Andromeda matters to us. After exploring all the technical details, the cosmic violence, and the distant future, it's worth stepping back to ask a more fundamental question. Why does Andromeda matter to us, here and now, on this small planet orbiting an ordinary star? Why should we care about a galaxy millions of light-years away that won't even collide with us for billions of years? The answer reveals something profound about human nature and our place in the universe. First, Andromeda represents the ultimate long-term perspective. In our daily lives, we worry about deadlines, bills, relationships, careers, things that matter on scales of days, months, or years. Even our most far-sighted planning, saving for retirement, worrying about climate change, preparing for our children's future, rarely extends beyond a century or two. Andromeda forces us to think on timescales of billions of years, to consider cosmic destinies that dwarf human history. This perspective is humbling, but also liberating. The petty concerns that dominate our thoughts shrink to insignificance when viewed against the backdrop of cosmic time. Second, Andromeda reminds us of our cosmic heritage. We are made of atoms forged in stars, scattered across space by supernovae, gathered into planets by gravity, and organized into living, thinking beings by billions of years of evolution. The iron in our blood, the calcium in our bones, the oxygen we breathe, all were created in stars that died long before the sun was born. Some of those atoms may have come from Andromeda itself, ejected into intergalactic space by ancient supernovae, and eventually incorporated into the gas cloud that formed our solar system. We are, quite literally, made of star stuff, and Andromeda's stars are our distant cousin. Third, studying Andromeda teaches us about our own galaxy and about galaxies in general. Because we're inside the Milky Way, it's difficult to see our galaxy's overall structure. We can't step outside to take a photograph or get an external view. Andromeda serves as a proxy, a nearby galaxy similar to our own that we can study in detail. By understanding Andromeda's structure, star formation, dark matter distribution, and history, we learn about the Milky Way and about the physical processes that govern all galaxies. Every discovery about Andromeda is also a discovery about ourselves. Fourth, the Andromeda-Milky Way collision illustrates the fundamentally violent and dynamic nature of the universe. The popular image of space as a serene, unchanging void couldn't be more wrong. Galaxies collide, stars explode, black holes devour matter. The universe is a place of constant change, destruction, and rebirth. Understanding this helps us appreciate that Earth's tranquility is an illusion, a temporary bubble of calm in a cosmos that operates on principles of energy, entropy, and transformation. We exist in a dynamic universe, and our survival depends on understanding and adapting to its realities. Fifth, Andromeda inspires wonder and curiosity, the twin engines of scientific discovery and human progress. When we look at Andromeda through a telescope or in photographs, we're not just seeing a pretty picture. We're witnessing an actual place, a massive galaxy filled with hundreds of billions of stars, many with their own planets, some possibly harboring life. The scale is incomprehensible, yet we can observe it, measure it, understand it. This capacity for understanding the universe is one of humanity's greatest achievements. It shows that despite our tiny size and brief existence, we can grasp cosmic truths, can decode the universe's secrets, can see across billions of light years and billions of years of time. Finally, Andromeda offers a vision of the future, both dark and beautiful. The collision and merger will destroy the spiral structures of both galaxies, end star formation, and create a giant elliptical graveyard. It's a reminder that nothing lasts forever, that even galaxies have lifetimes, that entropy always wins in the end. But it's also a reminder of the universe's creativity and resilience. The collision will trigger massive bursts of star formation, creating millions of new stars and planetary systems. It will scatter stars across vast distances, creating new cosmic environments. It will demonstrate that even in destruction, there is creation, that the universe is endlessly inventive in finding new ways to organize matter and energy. For those of us alive today, Andromeda is a symbol of the vastness, beauty, and mystery of the cosmos. It's a reminder that we're part of something immeasurably larger than ourselves, that our galaxy is just one among trillions, that Earth is a tiny stage in a universe so large it defies comprehension. Yet we can understand it. We can measure Andromeda's distance, map its structure, predict its future. We can see in Andromeda our own cosmic destiny. In 4.5 billion years, assuming any of our descendants still exist and remember, they will look up at a sky transformed, at a new galaxy being born from the ashes of two old ones, and they will see the culmination of a story we started telling today. They will see Milkomeda, and they will remember that once, long ago, there were two galaxies, and one of them was ours. That continuity, that connection across billions of years, is perhaps Andromeda's greatest gift to us: perspective, context, and a sense of our place in the infinite sweep of cosmic time. Before you go, drop a comment below telling us what fascinates you most about Andromeda. Is it the collision? The double nucleus? The fact that you can see it with your own eyes? And if you enjoyed this deep dive into our galactic neighbor, make sure to like this video, subscribe to the channel, and hit that notification bell so you don't miss our next journey through the cosmos. Keep looking up, keep asking questions, and remember that every time you see that faint smudge in the autumn sky, you're looking at our cosmic destiny. Until next time.